It all began with the appearance of a shocking mystery object. Believed to be an alien object, the comet-like body of Oumuamua created a frenzy, but this is not where it ends. It looks like they're here, in just 7 minutes ago, the James Webb Telescope made a shocking discovery of astronomical proportions. It has given us concrete signs of life. Join us as we talk about how the telescope promises to capture discoveries that will reshape our perception of the universe. This momentous event marks a significant milestone in our quest to unravel the mysteries of the cosmos and underscores the extraordinary capabilities of the James Webb Telescope. A step closer to aliens, humans were shocked at a cosmic rock that rushed through our solar system from beyond. Astronomers have found 2 interstellar objects that entered the solar system from different neighbors. Oumuamua was discovered in 2017, and Borisov was discovered in 2018, providing scientists with a tantalizing view into other planetary systems. However, because these objects emerge unexpectedly, astronomers must race to collect as many observations as possible during the brief period when they are close enough to investigate. Fortunately, NASA's recently launched James Webb Space Telescope will broaden that perspective. Christina Thomas, an astronomer at Northern Arizona University, stated that with Webb they can conduct intriguing scientific research at significantly fainter magnitudes or levels of brightness. Now, JWST unveils an Earth-sized alien world in orbit. In a cosmic milestone, the telescope has officially confirmed its first alien planet. And guess what? It's a rocky orb akin to our very own Earth. Why is this groundbreaking? The JWST's superpower lies in its ability to scrutinize distant planets, and this discovery is the first step toward unraveling the mysteries of this newfound celestial neighbor's atmosphere. What was the cosmic detective work at play? Scientists pointed the JWST's keen eye toward a star system that carried hints that a planet was situated a staggering 41 light-years away. TESS, NASA's pioneering spacecraft, initially teased us with the existence of this world, but it was the JWST's fresh data that sealed the deal. The planet, christened LHS 475b, whirls around its star, a diminutive, cooler version of our sun, every 2 days. Astonishingly, it's a few hundred degrees warmer than our cozy Earth, despite its proximity. The real curiosity lies in its atmosphere. Due to the star's smaller, cooler nature, there's potential for this planet to possess a shroud of gases. However, unlocking the secrets of LHS 475b's atmosphere is a puzzle that requires some time and patience. Aaron May from the Johns Hopkins University Applied Physics Laboratory, one of the minds behind this discovery, emphasized, "The telescope is so sensitive that it can easily detect a range of molecules, but we can't yet make any definitive conclusions about the planet's atmosphere." So far, the research team has eliminated a few possibilities. It seems that LHS 475b doesn't wear an atmosphere akin to Saturn's moon Titan, rich in thick layers of methane. Instead, there's a chance it could be enveloped in an atmosphere dominated by carbon dioxide. The team anticipates gathering more data during follow-up observations slated for the upcoming years. After all, they've been waiting to come across such a discovery for ages. So, what was the mechanism that led to this revelation? The JWST spotted this planet by meticulously observing changes in its star's luminance as it passed in front of the telescope's line of sight. These subtle fluctuations in starlight unveil critical details about the planet's orbit, size, and distinctive traits. These transits also serve as cosmic canvases, allowing scientists to paint a picture of the planet's atmosphere. By studying how light scatters when traversing this celestial envelope, scientists can start to decipher which molecules may be present in this newfound world. But don't think these claims and efforts to discover alien life are not serious because scientists came up with an intriguing way to prove to us how good JWST is. According to Ryan McDonald, an astrophysicist from the University of Michigan, it's almost as likely they didn't find it at all. And then there's the question of whether DMS is exclusively made by living things. One notable case involves Gliese 887, the brightest red dwarf in our observable sky, which potentially hosts a planet within its habitable zone, where conditions could be conducive to liquid water. However, the habitability of planets orbiting red dwarfs has remained uncertain due to limited knowledge regarding their composition. Previous research indicated that small exoplanets, particularly those with a diameter less than 4 times that of Earth, orbiting sun-like stars, were typically either rocky or gaseous. In this study, astrophysicists turned their attention to small planets circling closer, and hence brighter. Red dwarfs, as observed by NASA's Transiting Exoplanet Survey satellite. By leveraging methods such as observing planetary transits and measuring gravitational interactions between planet and star, the researchers gathered data on 34 exoplanets, enabling them to estimate densities and infer compositions. The findings categorized these exoplanets into 3 groups: 21 rocky, 7 gaseous, and notably, 6 of the newly identified watery type, composed of approximately equal parts rock and water, whether in liquid or ice form. The presence of so many water-rich worlds orbiting the most common star type in the galaxy was a surprise, according to study co-author Raphael Luque. This revelation carries immense significance for the quest to locate habitable planets. Formation models suggest that these small planets evolved through 3 distinct pathways. Rocky planets likely formed from relatively arid material close to their stars. In contrast, watery planets originated from icy material farther out, migrating inward over time. Gaseous planets, while also water-rich, probably began with greater mass, allowing them to accumulate hydrogen and helium atmospheres. According to Ryan McDonald, a JWST-savvy astrophysicist from the University of Michigan, it's almost as likely they didn't find it at all. And then there's the question of whether DMS is exclusively made by living things. On Earth, it's produced by marine algae and even released when you cook cabbage. But that doesn't necessarily mean it's a surefire sign of life elsewhere, explains Joe Barstow, an expert in planetary atmospheres at the Open University in the UK. Niku Madhusudan, from the University of Cambridge, part of the team behind the ocean planet Discovery, admits that the DMS finding is a bit up in the air. They decided to bring it up in the announcement because there's a faint but noticeable signal, and it could be a potential hint of life. The result is very tentative, but there still seems to be something there, he mentions. This whole situation showcases the excitement and challenges of hunting for signs of life on far-off worlds. The JWST is giving us a whole new way to peek at exoplanet atmospheres, and who knows what we'll find. But even with all this tech, Maggie Thompson, an astrophysicist from ETH Zurich, isn't sold on the idea of one smoking gun molecule for life. I don't think that there will ever be one molecule that if we see it, we will say yes, life, she predicts. Still, she's open to the idea of certain combos of molecules being a strong hint. With the JWST, there's hope we'll get some fascinating insights into atmospheres that might be bustling with biological activity. Regardless of whether K218b is teeming with little green men or not, this study is shouting from the rooftops. Hycean worlds are where it's at for sniffing out signs of extraterrestrial life. Madhusudan is still pretty pumped, saying that while we usually focus on smaller rocky planets, these larger Hycean worlds are way more cooperative for this kind of cosmic snooping. The jury's still out on how many of these Hycean worlds are out there. Oh, and props to JWST for flexing its cosmic muscles. The profound achievement of capturing such detailed insights into the atmosphere of K218b underscores the monumental capabilities of the James Webb Space Telescope. The level of precision attained here would have been beyond the reach of its predecessor, the Hubble telescope. JWST's extended wavelength range and unparalleled sensitivity are revelationary. It made this discovery with a fraction of the observations that would have been required by Hubble. This stark contrast in capabilities underscores the transformative leap in observational technology and reaffirms the indispensable role that JWST plays in advancing our understanding of the cosmos. The team's not done yet, though. They're planning another rendezvous with K218b, fingers crossed for more clues about extraterrestrial life. Madhusudan's feeling pretty optimistic, saying it could shake up our whole cosmic worldview. On one hand, JWST is guiding us towards more discoveries. This marvel of a telescope can pick up signals a whopping 100 times fainter than what Hubble can catch. Plus, it's a pro at monitoring much longer wavelengths, which means it's fantastic at nailing down certain molecular signatures. In the case of K2-18b, the JWST's keen eye determined that those signals previously pegged as water were telling us about the presence of methane. So, why has this molecule sparked such an interest? Let's take a look. The importance of methane, much like water on a planet's surface, serves as a tantalizing clue that a celestial body might be capable of hosting life. This is due to the molecule's relatively short lifespan in an atmosphere. Here on Earth, it typically transforms into water vapor and carbon dioxide within just 7 to 12 years. So, if scientists detect methane in a planet's atmosphere, it strongly suggests that something on that planet is actively producing it. On our home planet, life takes the lead in methane production. Nearly all of the methane here is biogenic, stemming from living organisms, primarily as a byproduct of processes like animal digestion or the decay of organic matter. Yet, it's worth noting that methane can also emerge from volcanic activity, be released during certain chemical reactions within rocks, or even appear after a comet or asteroid impact. Hence, the presence of methane alone isn't enough evidence to confidently claim a planet supports life. However, scientists like Thompson and her team have been delving into combinations of methane and other gases that might be more challenging to explain through geochemical processes alone. They've uncovered a potential biosignature, an upper atmosphere featuring methane and carbon dioxide, devoid of oxygen or hydrogen, and with minimal to no carbon monoxide. Models suggest this gas composition can arise when a planet's methane originates on its surface, a region where scientists believe life could potentially exist. As Thompson puts it, this set of observables would certainly be cause for great excitement. However, she emphasizes the need for extensive follow-up studies. Barstow concurs, highlighting the vast gaps in our understanding of the chemical reactions occurring within exoplanet atmospheres. It's crucial to exhaustively explore every conceivable source of a molecule before confidently attributing it to life. When it comes to K2-18b, the observed methane is unlikely to have a biogenic origin. Both past and current observations strongly suggest that the planet's atmosphere is predominantly composed of hydrogen. In such an environment, methane can be generated through photochemical reactions involving hydrogen and carbon. But wait, what about the water that scientists found on K2-18b? How significant a discovery is that? Water on K2-18b. The discovery of methane on K2-18b is undeniably intriguing, even though the implications are still being hashed out. What sets this apart is that it's not just methane they're seeing, it's also carbon dioxide, both hovering at around 1% concentration. Now, methane represents carbon in its simplest form, devoid of oxygen, while carbon dioxide is at the opposite end, brimming with oxygen per unit of carbon. This dual presence suggests a potential chemical imbalance in the atmosphere, opening doors to additional revelations. The team, led by Madhusudan, proposes that this disparity arises from a vast planetary ocean on K2-18b. While methane and carbon dioxide have been confidently detected, the absence of ammonia and water might raise eyebrows, especially for a world assumed to be rich in water. However, it's crucial to note that the JWST primarily probes the upper layers of an atmosphere. According to their model, water resides beneath the hydrogen, and the absence of ammonia aligns with this prediction. The ocean serves as a natural reservoir, effectively drawing ammonia out of the atmosphere. Arriving at this conclusion involved a complex analysis of JWST data, a process that's prompting caution among other scientists. The JWST relies on the transit method, where a planet passing in front of its star causes a slight dimming of the star's light. This reduction in brightness provides insights into the planet's size and the composition of its upper atmosphere. However, moving from raw JWST data to a list of identified gases is no walk in the park. Scientists generate a spectrum from the transit event and compare it with computer models simulating spectra under various planetary and atmospheric scenarios. Ryan McDonald explains that they explored millions of combinations of molecules and properties of planets, such as temperature and cloud coverage, until they found something consistent with the observations. Yet not all models yield identical outcomes. Ideally, researchers reconcile these differences through independent cross-checks using the same dataset. However, some JWST data isn't publicly available, as certain targeted observations remain exclusive to the collecting group for a year. The data for K2-18b's observations by Madhusudhan and the team will begin to be released next January 2024. Until then, much of the planetary research community holds a degree of uncertainty regarding these findings. MacDonald underlines that the ocean's conclusion hinges on the detection of methane and the calculation of its abundance. He notes that if independent teams, starting from the raw data, also spot the same methane and carbon dioxide features and measured the same concentrations, then they'll be much more assured that the discovery holds weight. Speaking of discoveries, Josti's mission to redefine our knowledge of space shows no signs of stopping. Secrets in the Kuiper Belt. Cosmic secrets in the Kuiper Belt are now all that scientists are talking about. In a cosmic revelation, the James Webb Space Telescope has unveiled the mysteries of three heavyweight champions of the Kuiper Belt: Sedna, Gongong, and Quaoar. These dwarf planets, once hidden in the abyss of space, are now under Webb's cosmic scrutiny. The Kuiper Belt, a cosmic treasure trove at the edge of our solar system, teems with icy enigmas, each holding clues to our solar system's epic saga. These Kuiper Belt objects, or trans-Neptunian objects, are celestial storytellers, revealing the dynamic history of planetary migrations and gravitational currents shaping our cosmic neighborhood. The James Webb Space Telescope, armed with its near-infrared spectrometer, steps up to decode these enigmatic giants. Sedna, Gongong, and Quaoar, while not household names, are cosmic heavyweights, each over 1,000 kilometers wide. They're the unsung heroes of the Kuiper Belt, and they have stories to tell. The Webb telescope's observations peel back layers of cosmic mystery. We've witnessed a cosmic ballet of ethane, acetylene, and ethylene, a chemical tango influenced by their cosmic neighborhood. Yet, this discovery raises more questions. How stable are these compounds? Could atmospheres swirl around these giants? It's a cosmic puzzle, waiting for us to solve. But there's more. This isn't a one-time occurrence. It's a revelation that's changing the history of Kuiper Belt objects and the trans-Neptunian region. We're piecing together a story that has shaped these cosmic visitors' fortunes for ages. The James Webb Space Telescope is more than a telescope. It's a cosmic time machine that's assisting us in rewriting the story of our cosmic backyard. So, what comes next? These discoveries pave the way for a better understanding of the genesis and evolution of celestial entities other than Neptune. It's a view inside the pages of a cosmic history book, recorded in the molecules and compounds of these distant giants. Except, we have one more shocking discovery. An unconventional planet. The discovery of the exoplanet. LTT 9779b challenges conventional understanding. This Neptune-sized celestial body, boasting metallic clouds and reflecting a staggering 80% of its host star's light, defies expectations. Positioned remarkably close to its brilliant star, T-Sensema B is a rarity, orbiting in a mere 19 hours. Link. A team of scientists uncovered that the planet's sunward side exhibits an albedo of 80%, surpassing any previously observed planetary reflectiveness. For comparison, Earth, despite its abundant water and highly reflective polar regions, reflects only around 30% of sunlight. The secret to LTT 9779b's remarkable albedo lies in its metallic cloud cover, predominantly composed of silicate and titanate, a titanium-containing salt. Initially, it was assumed that the planet's proximity to its star would prohibit cloud formation due to the extreme temperatures, exceeding 2,000 degrees Celsius. However, the high abundance of silicate and titanate gases in the atmosphere allows for the formation of liquid clouds, akin to condensation from a running shower. Moreover, these metallic clouds shed light on another enigma, the planet's size. Previously, all known ultra-short period planets were either gas giants, surpassing Jupiter's size, or rocky planets no larger than Earth. Thus, the existence of smaller gas giants like LTT 9779b so close to their host star was deemed improbable. Study co-author Vivian Parmentier aptly describes LTT 9779b as a planet that shouldn't exist, given conventional expectations. The reflective clouds serve as a shield, preventing excessive heating and atmospheric evaporation. Furthermore, their metallic composition lends weight, making the planet more resistant to being blown away by stellar winds. Despite its gleaming exterior, LTT 9779b likely started as a larger entity than Jupiter and has eroded over time, the researchers posit. While Venus once held the title for the brightest known planet, reflecting 75% of the Sun's light, LTT 9779b's astonishing 80% reflection now sets a new record. With its peculiar features, this exoplanet challenges our understanding of planetary formation and highlights the complexity and diversity of celestial bodies beyond our solar system. But the potential for life is unceasing. Gas crucial for life meet WASP-39b, the interstellar hotshot of our galaxy. It's not your run-of-the-mill planet. This one's a gas giant, like Jupiter, but scaled down to about 28% of its size. It's got some serious speed, orbiting its G-type star in just over 4 days. And get this, it's cozied up real close, about 0.0486 astronomical units from its star. Back in 2011, scientists dropped a bombshell. They found WASP-39b. Fast forward to July 2022, and it had a VIP visit from NASA's James Webb Space Telescope. Now, here's where it gets intriguing. The Webb telescope, with its cosmic eye, spotted something big, clear signs of carbon dioxide in the planet's atmosphere. This is groundbreaking stuff in our hunt for potential extraterrestrial life. Hold on to your seats because in November 2022, the science community spilled the beans, not just in one, but in 5 papers, revealing all the jaw-dropping discoveries about WASP-39b. They even dug into sulfur dioxide and starlight-induced chemical reactions happening up there. Now picture this. WASP-39b is a hot mess, literally. It's puffy, massive, and as toasty as an oven at around 1600 degrees Fahrenheit. It's a bit of a cosmic daredevil, orbiting super close to its star. But here's the kicker. Previous telescopes caught glimpses of its water vapor, sodium, and potassium vibes. But the Webb telescope, it took it up a notch by confirming the presence of carbon dioxide. So, WASP-39b isn't just any exoplanet. It's the lead actor in our cosmic drama, setting the stage for some mind-blowing discoveries. Buckle up, because the alien revelations might just be around the corner. But it isn't just planets eons away that are a surefire sign of life. Nearby, mysteries plague us, which JWST is keen on solving. Saturn's hope for life, the James Webb Space Telescope, has made a surprising discovery about Saturn's moon Enceladus. It detected a colossal plume of water shooting out from the small, icy moon, extending a whopping 6,000 miles into space. This plume is about 20 times wider than the diminutive moon itself. Enceladus has long been considered one of the most promising candidates in our solar system for potential extraterrestrial life. The recent observation by the James Webb Space Telescope suggests that this advanced telescope might play a crucial role in guiding scientists on how to search for signs of life on this moon. Back in 2005, NASA's Cassini mission initially detected water plumes emanating from Enceladus during a series of close flybys. However, at that time, scientists had only limited insight into the power of these geysers. The JWST has now provided a fresh perspective on these watery jets, allowing for a thorough examination of their composition. Geronimo Villanueva from NASA's Goddard Space Flight Center, who led the study, stated, "With the James Webb Telescope, we can measure water from far away and see the whole view for the first time." The JWST measurements unveiled that this torrent of water rushes out of Enceladus, a moon just 300 miles wide, 500 kilometers, at a speed of 79 gallons, 360 liters, per second. This rate is swift enough to fill an Olympic-sized swimming pool within a couple of hours, as per NASA's statement. Surprisingly, while the presence of water on Enceladus was anticipated, the scale of the emission observed by the Webb telescope far exceeded expectations. Villanueva remarked, "When we planned this, we thought we were going to see a little bit of water very close to the surface. We have never expected this type of emission of water." This discovery underscores the significant impact Enceladus, despite its minuscule size, has on the environment around the gas giant Saturn, which it orbits in less than 2 days. The water geyser generates an extensive watery cloud trailing behind the Moon, situated in Saturn's orbit, which extends towards the planet's other moons. Scientists are now eager to explore what else might be dispersed throughout the solar system due to this powerful spray. Previous analysis of Cassini data identified molecules in the Enceladus plume, such as methane, carbon, oxygen, and phosphorus, which could be potential indicators of life. Enceladus possesses the essential conditions for simple life forms to potentially emerge, with its liquid ocean sandwiched between a thick ice shell and a rocky core that serves as a source of nutrients. The Moon's proximity to Saturn subjects its core to immense gravitational forces, likely generating internal heat. This factor could potentially facilitate the chemical reactions necessary for microorganisms to develop. However, Villanueva mentioned that during its initial examination of this intriguing water world, the Webb telescope did not detect traces of these molecules. He expressed hope that if they are indeed present, future observations may yield more conclusive results. Either way, it seems that JWST's stellar potential will unearth more potential sources for life. Are you following NASA's journey to discovering concrete evidence of alien life?